All right, today we're going to unravel a real cosmic detective story. And it all starts not with some huge explosion, but with a whisper, a ghost in the machine, really. Something found years later, buried in a mountain of old data. A signal that would end up changing astronomy as we know it.
So, picture this. It's 2007. A grad student, David Narkovic, is working with his supervisor, Duncan Lorimer. And what are they doing? They're digging through old data from Australia's Parkes radio telescope. I mean, this data was from 2001. It was already 6 years old. And buried deep inside all that information was this. An incredibly powerful, but super brief, flash of radio waves. We're talking less than 5 milliseconds long. Blink, and you'd miss it.
So, what on earth was this powerful, fleeting signal? Was it just a glitch in the system? You know, some random interference? Maybe someone microwaving their lunch nearby? Or was it something else entirely? This was the brand new mystery that astronomers suddenly had on their hands.
So, to figure it out, they had to start looking for clues. And the very first, and maybe the most important clue, was this sort of cosmic fingerprint. A dead giveaway that this signal had traveled a very, very long way to get to us. Okay, so this key clue is a phenomenon called dispersion. Basically, as a radio signal travels through all that thin gas between stars and galaxies, it gets stretched out just a tiny bit. See, the high-frequency waves in the signal, they travel just a little bit faster than the low-frequency waves.
The best way to think about it is like a race. Imagine all the different frequencies in the signal start their journey at the exact same moment. The high frequencies, they're the sprinters. They're fast. The low frequencies are the marathon runners, a little bit slower. So, by the time they all get to the finish line, which is our telescope, the sprinters arrive first. And just a split second later, the marathon runners cross the line. And here's the cool part. The bigger that delay, the farther the race was. It tells us exactly how far the signal has traveled. So if we go back and look at that original signal, you can see it, that perfect downward sweeping curve. That's the fingerprint. The high frequencies are up at the top, arriving first, and the low frequencies are at the bottom, arriving later. This was no glitch. This thing perfectly matched the laws of physics for dispersion. It was, without a doubt, a real signal from deep space. Okay, so we've established it's real. Now the big question is, where did it come from? And just like any good detective story, the next step is to start ruling out the suspects, one by one.
Well, you always have to start with the most obvious culprit, right? The one closest to home. Could this signal just be from Earth?
Yeah, the evidence against an earthly origin was pretty overwhelming. First off, that dispersion curve, it's really, really hard to fake something that perfect. Second, this was a one-time thing. Most interference we see on Earth tends to repeat itself. Third, it only showed up in 3 very specific adjacent beams of the telescope, not all over the place. And finally, the telescope was pointed almost straight up, which makes it super unlikely that something on the ground caused it. So, the big takeaway here? The call was not coming from inside the house.
Okay, so it's from space. That's a huge step. But is it from our own backyard? You know, somewhere inside our own Milky Way galaxy?
This is where that delay we talked about, what scientists call the dispersion measure, or DM, becomes the smoking gun. The DM for this burst was measured at 375. But here's the thing. Scientists calculated the absolute maximum amount of dispersion our entire galaxy could possibly contribute along that line of sight. And that number? Just 25. Our burst's number was 375. There's just no way it came from inside the Milky Way. It had to have traveled through way, way more stuff than our galaxy has to offer. So suspect number 2 is officially clear.
But hang on a second. The telescope was pointed at something specific, right? It was studying a nearby galaxy, the Small Magellanic Cloud, or SMC for short. So maybe it came from there? I mean, that would explain all that extra dispersion.
Let's take a look at the sky map. You can see the main part of the Small Magellanic Cloud right here. But the burst? That's the little square. It's a full 3 degrees away from the galaxy. It's out in what looks like empty space. So it doesn't seem to be connected to the SMC at all.
And if you need one more piece of evidence, here's the final nail in the coffin for that theory. The highest dispersion measure we've ever seen from anything inside the Small Magellanic Cloud is about 205. Our mystery burst, 375. It's just way too high. There's no way it came from the SMC.
So let's recap. It's not from Earth, it's not from our own galaxy, and it's not from the nearby galaxy we were looking at. I mean, we've run out of local suspects. And you know what they say? Once you eliminate the impossible, whatever is left, no matter how improbable, must be the truth.
And that truth? Well, it was absolutely staggering. The signal had to be coming from outside our galaxy. And not just from a little bit outside, but from way, way beyond.
So the scientists did the math. They took the total dispersion, 375, and subtracted the part from our own galaxy, which was 25. That left them with the amount of stuff the signal traveled through in intergalactic space. And the distance they calculated from that? About 1 gigaparsec.
Now, what is a gigaparsec? Well, it's over 3 billion light years. To put that into perspective for you, this signal started its journey toward us before the first multicellular life even evolved here on Earth. It traveled through the empty void for 3 billion years before it finally hit that telescope dish in Australia back in 2001. Just incredible.
And a team, they knew right away how huge this was. In their actual discovery paper, they put it very simply. This burst, they said, represents an entirely new phenomenon. This wasn't just some weird, known star doing something funny. This was something nobody had ever seen before.
So the discovery of what we now call the Lorimer burst solved one mystery, where it came from, but it blew the doors open to a dozen more. The biggest one being, what in the universe could create such a powerful flash from so far away?
Naturally, the team went back and looked at that same patch of sky again and again. For a whopping 90 hours, they pointed the telescope right back there and they found absolutely nothing. No repeats. This told them it probably wasn't from something that flashes over and over, like a pulsar. No, this was likely a one-time cataclysmic event, something that probably destroyed whatever created it.
And here's the part that will really blow your mind. Based on the tiny patch of sky they were looking at and for how short a time they saw it, the team did a quick calculation. They estimated that hundreds of these things, maybe around 400 of them, could be going off all over the sky every single day. The universe was filled with these flashes. We just never knew how to look for them before.
So what could cause something so powerful? The theories started flying, and they were wild. Could it be two neutron stars colliding? Maybe the final gasp of an evaporating black hole? Or was it something completely unknown to physics? A whole new type of cosmic event? The age of studying these things, what we now call fast radio bursts, had officially begun.
You know, the story of the Lorimer burst is just such a great reminder that we have barely scratched the surface of what's out there. The universe is just full of secrets. And it really makes you wonder, right? What other incredible discoveries are just sitting there, hiding in plain sight, just waiting in some old data archive for the right person to come along and find them?